Today, I'm going to explain frequency response of RC lag lead compensator network. So first of all, what is actually compensators means? So let us see this theory part. The control systems are actually designed to perform specific tasks. So the aim is you have to achieve uh, performance should be maximum. Okay, due to some reasons, if the performance is not good, so we can improve the performance by adding compensator network. The compensator for a plant, you can add either electrical or mechanical or hydraulic, pneumatic or other type of device or the network you can add, and you can increase the performance of that system. In control system, compensation is required in the following situation. First one, when the system is absolutely unstable, then compensation is required to stabilize the system and has to meet the desired performance. When the system, second one is when the system is stable, the compensation is provided to obtain the desired performance. So we need compensation network for these two purposes. So we can have three types of compensator: lag compensator, lead compensator, a lag lead compensator. So for your syllabus, lag lead is given. So let us see what is actually lead compensator and lag compensator. Finally, I will explain what is lag lead. So this is the diagram of a lag compensator. Okay, this is a electrical network. So here we have different types of compensator circuit. The compensator circuit may be electrical, mechanical. No, so we are going to study electrical compensator circuit. So this is lag compensator. So in the lag compensator, we are using R1 and R2 as shown in figure. We are adding one capacitor in series with R2. So input is Vi of S, V naught is V naught, output is V naught of S, and transfer function is V naught of S by V of S. So you write in frequency domain. So resistance remains resistance only. This capacitor is replaced by 1 by SC. Now if you draw a, if you derive expression for output transfer function, okay, V naught by Vi of S transfer function. So you're going to get V naught of S by Vi of S is equal to this. Okay, 1 by alpha S into 1 by 2 divided by S plus 1 by alpha t, where tau is R2 into C, because C is connected in series with R2. So tau is R2 into C, and alpha is equal to R1 plus R2 divided by R2. So substitute S is equal to j omega, you're going to get this. So from this transfer function, you have to understand. So in the numerator, we have S plus 1 by 2. So uh, the lag compensator has one pole at 1 by minus 1 by 2, and in the denominator we have alpha t, 1 by alpha t. So 1 0 at 1 minus 1 by 2. Okay, so we know that phase of the output sinusoidal signal is equal to the sum of phase angle of the input sinusoidal signal and transfer function. So this is the formula for phase angle. Phase angle phi is equal to tan inverse of omega 2 minus tan inverse of alpha omega 2. So it is a sum of this plus this. So in order to produce phase lag at the output of this compensator, phase angle of the transfer function should be negative, and this is possible only when alpha is greater than 1. And in the lead compensator, actually here R2 is that capacitor. Instead of here we have to connect parallel to the R1. So this is a lead compensator. If I connect capacitor in series here, it becomes lead compensator. So in the lead compensator is an electrical network which produces sinusoidal output having phase lead when the sinusoidal input is applied. Lead compensator circuit in S domain is shown in figure. This is R1. Capacitor is connected in parallel with R1. And for this also you have to write transfer function V naught of S by V of S. So V naught of S by V of S is equal to the simplification. You can refer any other textbook. So you're going to get, for simplification, beta into S2 plus 1 divided by beta S2 plus 1, where 2 is R1 to C, because C is connected in parallel with R1. So 2 is R1C, and beta is R2 divided by R1 plus R2. So from this, in the numerator, you can see that one pole is presented minus 1, 1 by beta, and 0 at minus 1 by beta 2. So here also phase angle is equal to tan inverse of omega 2 minus tan inverse of beta omega 2. So here also phase angle is equal to sum of phase angle of the input and phase of the transfer function. So in order to produce phase lead of the output of the compensator, phase angle of the transfer function should be positive here, and this is possible only when beta lies between 0 to 1. So now we'll go to the actual for your syllabus lag lead compensator you have to simulate. So lag lead compensator circuit is you have to mix both the lag and lead compensator network. So that is you have to connect one capacitor in parallel with R1 and capacitor in series with R2. So this is actually uh, this is lead. Okay, if you write it, this is lead, this is lag. So here this is lead. This part will provide lead. This is lag. So we can call it as lag lead compensator circuit. Okay, now lag lead compensator is an electrical network which produces phase lag at one frequency region and phase lead at another frequency region. It is a combination of both lag and lead compensator. Lag lead compensator circuit in the S domain is as shown in figure. C is connected parallel with R1, C2 is connected series with R2, and transfer function for this also V naught of S by VA of S is given by this transfer. So if you derive, you can refer any textbooks, you will find this formula. After that, by simplifying that, you will get like this: V naught of S by VA of S is equal to S plus 1 by tau 1, S plus 1 by tau 2, S plus 1 by beta tau 1, S plus 1 by alpha T2, where tau 1 is R1 into C1, tau 2 is R2 into C2. So now we will see effect of lead and lead lag compensation on frequency response, because today we are going to do frequency response of lag lead compensator network. So necessity of compensation is, I will repeat once again, in order to obtain the desired performance of the system, we use compensating network. Compensating networks are applied to the system in the form of feed forward booth. Compensate a unstable system to make it stable. Compensating network is used to minimize the overshoot. Compensating network increases the steady state accuracy of the system. So for lag compensator, you're going to get frequency response of like this. This is a model graph. We'll verify whether you are doing the same thing or not. For lead, for lead the network, you are going to get model graph of like this, board plot and frequency plot. And the last one, effect of lead lag compensator is you have to write the circuit, and if you execute, you are going to get that graph is missing here. So I will show you that in the simulation only. So we will see the advantage and disadvantage of different circuits. So this is first one is lag compensator. So in the lag compensator, this is a pole at minus 1 by beta T, and 0 at 1 by tau, beta tau. Okay. So you are going to get like this. So advantage effect of phase lag compensation is gain crossover frequency is going to increase, bandwidth is going to decrease, phase margin will increase. Advantage of phase lag compensation is phase lag compensator allows frequency and high frequency are attenuated. It allows low frequency and high frequencies are attenuated. So that means it acts as a low pass frequency. Okay. Due to presence of phase lag compensation, steady state accuracy increases. So drawback of phase lag compensation is due to presence of phase lag compensation, speed of the system is going to decrease. That is the effect of phase lag compensation. So now is phase lead. So in the phase lead, you are having pole at minus 1 by alpha t, alpha 2, and 0 at 1 by 2, minus 1 by 2. This is the response. You can see by seeing the response, it is allowing high frequencies, suppressing low frequencies. So it is acts as a high pass filter and is a phase angle response. So advantage of phase lead is due to presence of phase lead network, the speed of the system is going to increase, but you shift the gain crossover frequency to the higher value. Due to presence of high lead compensation, maximum overshoot of the system is decreases. So drawback or disadvantage of phase lead is steady state error is not improved. So lead is having some advantage, lag is adding some advantage. So if you combine both lead and lag, so you are going to get better response. So advantage of phase lag lead compensation is due to presence of phase lag and lead network, the speed of the system is going to increase because it shifts gain crossover frequency to higher value. Due to presence of lag lead network, accuracy is also increases. So now we'll do one by one. So open MultiSim tool. Okay, this is design part, you can refer manual. Okay, so you have to pick this AC voltage source by going to place component, go to AC in the source. Okay, group is source, signal voltage source, AC voltage. If you go and place, you'll get like this. Okay, double click and change it to 10 kilo, sorry, 10 volts, peak to peak, 2 kilohertz. Okay, after that, you go to place component, place one resistor. It is available in basic. Place resistor. Okay, how many resistor you have to place? Like this, you have to place. One more you can place. If you want to rotate, you can place like this. I already connected the circuit. I am just explaining how to place a component. So double click and you can change the values to 3 kilo ohm. Okay, you can change this one to 3 kilo ohm like this. So like that, you have to place one resistor here, one resistor here. Double click and change the value to 225 ohms. So I'm deleting here because I already connected, but you people should write once again this. Okay, so place voltage, AC voltage source here, resistor here, and one capacitor here. So capacitor is also available in place component. The basic capacitor is okay, in the right, and you can place and you can change the values to micro. Micro means you have to type U. Okay, you can check, find one micro like this. You can type, and after that you have to make the connection as shown in figure, and you have to place one probe here. Probes are available here. Okay, you can go to place probes also, it is there. Go to place probe, voltage probe. Like this, you can place. You have to place on the wire. Okay, I placed one probe here, and R1 in series, R1 in parallel with C1. You have to make the connection and you have to place one ground. Ground is available in place component sources. So here our sources ground. So you have to place and you have to make the connection as shown in the figure. After that, we are actually we have to find out frequency response. You have to find out frequency response of this. So go to simulate, analysis and simulation. So go to AC sweep, starting frequency 10 hertz and stop frequency 1 megahertz. Okay, sweep type is decade because it is logarithm and output is if you place probe automatically it will take that probe value. If it is not there, you have to select that value and you have to add here. If I select, you have to measure voltage across R2 no. So V across R2 is there somewhere here. Voltage across R2 you have to add here and you have to plot that. So now it is voltage across PR1 means voltage across resistor R2 only. So now output is this frequency range is 10 hertz to 1 megahertz. So now run this. So this is the response you are getting. So this is the button to make change the color to 0, background white or black. Okay. So you are going to get this like a okay. This is like high pass filter. Low frequencies are attenuated, high frequencies are passed. So if you take 3 dB less here, you are going to get somewhere here cutoff frequency. Okay, you can refer the design part here. This is a circuit. 10 volts peak to peak you have to give R1, C1, R2. So you have to find out what is the value of R1, R2, C value. By considering C, we are assuming as 0.1 microfarad. Okay. Then by using that formula, you have to design the value of F is 2 kilohertz. Okay. F is 2 kilohertz. Phase margin is 60 degree. So for the degree, value of R1 and R2, C is 0.1 microfarad. R1, R2, you're going to get the value of what I used here. Okay, in the circuit diagram, R1, R2 is 3 kilo ohm and 224 ohms you're going to get. So this is actually, you're going to get the model graph is like this. Okay, see here, you're going to get like this and phase angle is like this. So in the simulation also, we are getting same thing. Same thing. So this is phase lead compensator. So now lag compensator is same. You have to connect like this. Okay. That capacitor, you instead of connecting parallel to R1, you connect in series with R2 and remaining procedures are same. Okay. Again, go to AC sweep, simulate, analysis and simulation. AC sweep starting is 10 hertz to 1 megahertz. Select linear or anything. Let us see what happens if it is linear. Output is VFP only. So simulate. So you are going to get it is like high pass filter, low pass filter. Low frequencies are not attenuated, high frequency are attenuated. So it is allowing only low frequencies to pass. So you're going to get phase reference, phase angle, phase response as like this. Now, in the lag, it is allowing low frequencies and it is attenuating high frequency. But in the lead, it is actually high pass filter. It is allowing high pass, high frequencies and attenuating low frequencies. Now, if I combine both, okay, you are going to get this. Now we have this is actually there in the syllabus lag lead compensator. Okay, we should get like this model graph. So now this is the actual circuit diagram. For your syllabus, only this much is there, but without knowing what is lag, what is lead compensator, you'll not understand. So that's why I explained those two also. So here you have to rig up the circuit as shown in figure. You get the component of AC voltage source by placing place component. Go to sources, signal voltage sources, AC voltage. You click OK. Change the value to 5 volts peak to peak. I can select 1 kilowatts also, no problem, because we are taking frequency response. No, you can take any value, no problem. You can type 1 kilo also, no problem, because we are not actually plotting frequency from the one particular frequency. We are plotting for different frequencies. Okay. So now, if you want to see for one particular frequency, so what is the phase response? You have to connect one oscilloscope, and I will show you that one. Okay, can change this one to 500 hertz also. So now for the frequency, you connect on two resistors, two capacitors. Capacitors values are 0.01 microfarad. Here also 0.01 microfarad. R1 is 10 kilo ohm, R2 is 2.7 kilo ohm. And here also you have to connect one probe, voltage probe, place probe. In MultiSim 14.1 or 2, it is available here only. Place probe. In MultiSim 11 and all, the right side corner arrow mark will be there. From there, you have to pick the probe. So now I will execute frequency response, simulate analysis and simulation. Starting frequency is 10 hertz, ending frequency is 1 megahertz. Okay. Now I will run this. You're going to get like this. See, this part is high pass. It is actually low pass filter, and this is high pass filter. It is combination of lag lead. So you're getting both response combined. And this is also one is like this, another is like this. Now both will combine. You're going to get like this. Individual response of both you observe. Individual response of, see, this is low pass filter. Its response is downwards here, and opposite in the here. So now it is combining both this and this. So now I'll show you what is how to find the this one. This is just pattern. So for this, okay, for this, we have to connect one oscilloscope. One input is connected to output side. Another channel input is connected to input side. Let us this color segment is blue or green. Green is output, and I'm giving input as some blue color. And any one ground you have to make. You can ground both the channels. Okay. Red is grounded to this ground, common ground. Now, to find the phase shift at particular frequency, we have to find phase shift. So don't go for AC sweep. So go to simulate analysis. You have to go for interactive. This interactive, okay, only one particular simulation. Okay, run now. So now actually input is given with a single frequency of 500 hertz. At that particular frequency, what is the output we are getting in the oscilloscope? You have to check. So you can see here. So there is a little bit phase shift between input and output now. There is a small phase shift between input and output. Okay, now you have to click A slash B. That is channel A versus channel B. Voltage versus voltage. Output voltage versus input voltage. So you're going to get this. This is called as Lyserg's pattern. So how to find the phase shift? How to find the phase shift? So you have to find out. This is the diagram. You have to find out intersecting. Okay, intersection between these and this. What is the how many division it is collecting and maximum. That is here from here to here it is 0.2. Here also 0.2. Each division is actually 5 subdivisions are there. So here it is 1 means 0.2, 0.2, 0.2, 0.2 here. So 0.2 here, 0.2 here. Total it is 0.4 and maximum is it is I think zero point 0.9 here also 0.9, not actually exactly 1. It is approximately 0.9. So 0.9 and 0.9 peak to peak is 1.8. So 0.4 divided by 1.8 sine inverse of fifth sine inverse of 0.4. This one, you know, why it is intersecting at 0.2 here, 0.2 here. So total width is 0.4 and this height, maximum height here to here. Here to here it is 0.9. Here to here it is 0.9. So divided by 1.8. 0.9 plus 0.9 is 1.8. Sine inverse of 0.4 divided by 1.8. That is the phase shift. It is 12 degrees. Similarly, you change the frequency. Change the frequency to some other frequency. For example, 1500. Stop and rerun. Once again, double click on this. You're going to get a little bit less. Okay. Again, you can change this frequency to maximum frequency. 7,500. Let us see what happens. It's coming like this. This is reducing. Okay. Now it is almost 0.6 and 0.6 sine inverse of zero point 0.4 divided by 1.2. Okay. Similarly, the Lyserg's pattern is opposite this side. Then you have to take 180 degree minus sine inverse of y1 by y. This is if it is right side of this here in the first quadrant, then it is y1 by y2. Suppose if it is left side, figure B, then phase shift is equal to 180 degree minus sine inverse of y1 by y2. So you can try for all the values. For example, I will give another, let me give some higher frequencies. 50,000 I'll give, let's check for 50,000 frequency. You're getting, see, this is the frequency response. This is how to check the frequency. Remember, to find the frequency response, you have to go for simulate, simulate analysis and AC sweep. To find the phase angle, okay, don't run AC sweep. You have to calculate phase angle using Lissajous pattern. For each frequency, you have to change here manually and you have to find out what is y1 and y2, sine inverse of y1 by y2. Yeah. To find the overall frequency response of the system, you can keep this frequency any one and you have to plot frequency analysis and simulation, then AC sweep, starting frequency 10 hertz, top frequency 1 megahertz. This is can be decade and this is vertical scale or decibel, anything you can take. I checked all the thing. For in all the things, same thing is coming. I am placing in decibel. Let me see what happened. And output should be voltage across probe, where probe is connected across the output and run it. So you're going to get like this. Okay, this is frequency response of lag lead compensator network. So it is a combination of low pass filter and high pass filter, lag compensator as well as lead compensator, both merged, okay, combined. So this phase also both response will be combined and magnitude response also both is combined. Okay, thank you.